The general trend of increasing first ionization energy across a period is driven by an increasing effective nuclear charge, which binds the valence electrons more tightly to the nucleus. However, specific discontinuities occur between groups 2 and 13 and 15 and 16 that provide direct evidence for the existence of energy sublevels. At group 13, the electron is removed from a p sublevel rather than an s sublevel. Because the p orbital is higher in energy and better shielded from the nucleus by the s electrons, less energy is required to remove it despite the increase in nuclear charge. At group 16, the discontinuity arises due to the onset of electron pairing within the p sublevel. When two electrons occupy the same orbital, the localized electrostatic repulsion between them increases the potential energy of those specific electrons, making the first one significantly easier to remove than if it were in a singly occupied orbital. These dips in the data confirm that electrons are not in a single uniform shell, but are organized into distinct sublevels with varying energy levels and spatial distributions. The unique chemistry of transition elements stems from their incomplete d sublevels, which allow for an expansive range of physical and chemical behaviors. Because the energy levels of the d and s orbitals are remarkably close, these metals can lose different numbers of electrons to exhibit variable oxidation states, such as iron existing as +2 or +3, and manganese reaching all the way up to +7. This electronic flexibility, combined with available empty d orbitals, allows transition metals to act as Lewis acids in the formation of complex ions, where they coordinate with ligands like NH3 and Cl-. When these complexes form, the d orbitals split in energy, and electronic transitions between these split levels absorb visible light, leading to the formation of colored compounds, a sharp contrast to the white or colorless compounds of the s-block elements. Furthermore, the presence of unpaired electrons in these sublevels provides distinct magnetic properties, ranging from the paramagnetism of manganese ions to the strong ferromagnetism of solid cobalt and nickel. These electronic characteristics also dictate the metal's structural and functional utility. The participation of d electrons in delocalized metallic bonding results in extremely strong interatomic forces and high melting points, exemplified by tungsten's ability to withstand temperatures of over 3,400 degrees Celsius. These properties are harnessed in catalytic properties, where the metals provide an active surface for reactant absorption and utilize their variable oxidation states to lower activation energy. A practical application is the catalytic converter, which employs transition metals like platinum, palladium, and rhodium to treat exhaust gases. These catalysts facilitate the reduction of nitrogen oxides and the oxidation of carbon monoxide by temporarily bonding with these gas molecules on their surface. Because of their high thermal stability, these metals can operate efficiently within the intense heat of an engine's exhaust system, ensuring that pollutants are converted into less harmful substances like N2 and CO2 without the catalyst itself being consumed or melted. We talked about variable oxidation states of transition metals already, but let's dive deeper into why transition metals are unique in this case. If we take a look at an element like potassium, which is not a transition metal, it will generally take one oxidation state of +1. It does this because losing that single electron will drop its electron configuration to that of argon, making it very stable. To remove another electron from this configuration would take a lot of energy. So potassium sits at +1. We can contrast this with manganese. Manganese is a transition metal and has outer electrons in the 4s orbital and 3d orbitals. The full configuration looks like this. The key thing to note here is that the energy levels of the 4s orbitals and the 3d orbitals are very close. This means that the successive ionization of elements like manganese can happen easier, which leads to varying oxidation states. For example, with manganese, 2 electrons can be ionized from the 4s orbital, which leaves manganese with a +2 charge. Note here that while the 4s orbitals are lower energy initially, when the d orbitals fill up, the energy levels drop below the 4s, leaving them with higher energy values, meaning they will be removed first when forming cations. This is important to know when drawing out electron configuration diagrams. In addition to the +2 charge, all 7 electrons from the 4s orbital and 3d orbitals can be ionized, leaving manganese with a +7 charge. Both of these are stable and can be found in compounds. In fact, manganese oxidation states can be anywhere between +2 and +7 due to the variability of electrons that can be removed from the 4s and 3d orbitals. This is unique to manganese, making it the element with the highest number of oxidation states among among the first period transition metals. For the exam, you need to understand why these transition elements have different oxidation states and also how to deduce their electron configurations in the different states. Let's take manganese with a +5 charge as an example. What would the electron configuration of this cation look like? Take a second and draw it out on your paper. We need to remove 5 electrons to get to this charge, so we start by removing 2 from the 4s orbital, and then another 3 from the 3d orbitals. This will leave us with a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, or a condensed notation of argon 3d2. As a final note, we have to talk about another cool property of transition metals, which is their ability to create vibrant colors when they create coordinate bonds with ligands in what is called a transition element complex. A transition element complex consists of a central, positively charged transition metal ion, or atom, surrounded by molecules or ions called ligands, which donate lone pairs of electrons to form coordination bonds. These coordination covalent bonds are different because both shared electrons originate from the same atom, known as the donor, and are shared with the accepting atom, known as the acceptor. This type of bond is represented by an arrow pointing from the donor to the acceptor. The donation of the electron pair from the ligand to the open d orbital of the metal creates an electrostatic field around the metal. As the ligand's electron pairs approach the metal along specific axes, they repel the electrons already present in the metal's d orbitals. This repulsion causes the previously degenerate d orbitals to split into different energy levels. Now this is important because it is the split in the energy that creates the vibrant colors we see. Let's talk about why this happens. The split creates 2 distinct energy levels, one that is higher and one that is lower, with an energy gap that is dependent upon a few factors such as the nature of the ligand, the oxidation state of the metal, and the geometry of the complex, to name a few. When a photon of visible light passes through the complex, it can absorb enough energy from the light to promote a lower energy d orbital electron to be briefly bumped up to a higher energy position. The energy that is absorbed for this to occur is equal to the magnitude of the energy gap. But as this amount of energy is absorbed from the white light, the unabsorbed remaining wavelengths that are left are transmitted out of the complex and can end up hitting our eyes, which we can interpret as still within the visible spectrum as being a specific color. So how do we know what color will be transmitted out of these transition metal complexes? We can use a color wheel to figure it out. On a standard color wheel, complementary colors are positioned directly opposite one another. As the transition metal complex absorbs a specific band of light within the visible spectrum that is determined by the energy gap, the color we perceive is the opposite or complementary color on the wheel created from the leftover visible light frequencies. For example, potassium permanganate appears purple because it primarily absorbs green and yellow light while transmitting red and blue light. Our eyes perceive the mixture of transmitted red and blue wavelengths as deep purple or magenta. The concept of the color wheel can be connected to the physical properties of the complex with 2 different equations, both of which we have already seen, but let's go over them again just as a refresher. The first equation is C equals F times lambda. C represents the speed of light in a vacuum, which is a constant value of approximately 3.0 times 10 to the 8th meters per second. F is the frequency of the wave, and lambda is the wavelength. Next is E equals H times F. This equation is called the Planck relation or the Planck-Einstein relation and is used to understand and analyze the energy associated with electromagnetic radiation. E represents the energy of a photon, a particle of light. H is Planck's constant, a fundamental constant of nature, and F is the frequency of the electromagnetic radiation. Let's go through an example question of how they relate to our color wheel and the vibrant colors produced by transition element complexes. Here's our scenario. The hexa-aqua-vanadium-3 ion appears green in aqueous solution. The color is observed because the complex absorbs a specific wavelength of visible light, which promotes an electron between the split d orbitals. Using the color wheel, determine the approximate wavelength of the light that is being absorbed by the ion complex. Calculate the energy difference between the d orbitals in joules based on the absorbed wavelength you determined. Feel free to pause the video and give these 2 questions a shot on your own. Okay, now that you're ready, let's go through the answers and talk about how to approach them. For the first part, we can use a color wheel to estimate the absorbed wavelength based on the color given. Because the color appears green to our eyes, the absorbed wavelengths will be opposite of that on the color wheel and be in the red range. We can estimate the absorbed wavelength to be around 670 nanometers. From there, we can take our estimated wavelength, convert nanometers into meters, and use our two equations to determine the energy difference. We first plug our wavelength into the first equation to get frequency, and then use that frequency value in the second equation to calculate the energy. Follow along with the animation to see the final answer.